This is the lecture for Wednesday, March 25th. Today we'll be continuing our discussion of quantum chromodynamics, but we will start off with quantum electrodynamics. So here is the Lagrange density for quantum electrodynamics. The Lagrange density meaning that the thing, what's called the action, the thing that we want to minimize, is the integral of the Lagrange density, where d for x is just the integral over the x0 component, x1 component, x2 component, x3 component. And I'm using this relativistic notation where 0 signifies the time component, 1, 2, and 3 are the spatial components. Okay, so when I write mu, it can be the index, Lorentz index 0, 1, 2, and 3. We have time and space components here. Okay, so let's take apart these various terms. So first of all, this psi e for the electron is the electron quantum field. And so this psi e is a 4-component column vector. That's implicit in this notation here. And these individual terms in the column vector, they will involve some linear combination of the annihilation operator for an electron and creation operator for the positron. The psi e bar is going to be a row vector, a 4-component row vector for where each of these terms will be some linear combination of the annihilation operator for the positron or the creation operator for the electron. Now, this gamma mu is what are called Dirac matrices. And they are 4x4 matrices. So there's, for each value of mu, so mu is again 0, 1, 2, and 3, for each of these cases we have a 4x4 matrix. And all this matrix structures do for you is make sure that we have Lorentz symmetry being respected by the interactions and the physics described by this Lagrange density. Okay, now let's carry on to describe all the other terms here. So this a mu is the field operator, the quantum field operator for the photon. And it has this index mu that can be 0, 1, 2, and 3, I just already mentioned. And the photon field will have some linear combination of annihilation operators for the photon, as well as creation operators for the photon. The photon, by the way, is its own antiparticle. Now, this term here is the mass term for the electron. Me is the mass of the electron. This term here is gives you the description of a non-interacting photon. So F mu nu here is the derivative d mu a nu minus d nu a mu. And hopefully this is already familiar to you as the electromagnetic field tensor. If I have mu equals 0 and mu equals 1, 2, or 3, we end up getting an electric field. If mu is equal to 1, 2, and 3, and mu is either 1, 2, and 3, we end up getting the magnetic field. Now, there's some notation I should mention. So I told you that these guys are, a mu's are Dirac matrices. These guys are called the Dirac 4-spinors. Okay, the psi and the psi bar, 4-spinors. There's also some notation here called Einstein's notation. If you see a index that's upper and lower, the same index upper, lower and upper, there's an implicit summation over that index. Now, I should tell you the difference between the upper and the lower indices. So, if I have a lower, let's go this way. If I have an upper index, it will be equal to the lower index if mu is equal to 0, or it's equal to minus a mu lower index if mu is equal to 1, 2, or 3. So raising or lowering the indices does nothing if mu is equal to 0, but it gives you a minus sign if mu is equal to 1, 2, or 3. The last thing I should mention for this Lagrangian is that there's this coupling here, okay? And so you're probably familiar with this fine structure constant as being e squared over 4 pi, and so I can write e in terms of alpha as the square root of 4 pi alpha. And this d mu is, of course, just the derivative acting on psi e. All right, now this coupling of the photon field, if you look at this photon field, it couples to this combination psi bar I, that gives me a minus sign, gamma mu e psi e. So I have something proportional to this e psi bar e gamma mu psi e. And that's what's called the current density of the electron. And the photon couples to this guy here, as you might expect. All right? Now, this rather interesting structure to the electron is related to what's called a gauge symmetry. Okay, so there's a gauge symmetry. And the idea of a gauge symmetry is that you make some transformation to the fields that's different at various points in space and time. Okay, the gauge symmetry in this particular case is a U1 gauge symmetry. So remember, U1 means a unitary 1 by 1 matrix. So essentially e to the I theta. Okay. But to make it a gauge symmetry, it's going to actually be e to the I theta of x. So it will be a function of x. Now, in order to make this work, though, so the idea is that psi of x will go to this e to the I theta of x psi of x. Now, everything would be fine except for the fact that there's a derivative here that acts on psi e. So if I make this transformation, there will be the phase acting on psi, there will be sort of the opposite phase acting on psi bar. They should cancel out, except when the derivative acts on this theta term here, I get an extra annoying term that makes the Lagrangian not stay the same under this gauge symmetry. However, this a mu that comes in sort of in a partnership with d mu comes in to save us if a mu of x transforms in this way. It is to a mu of x minus 1 over e d mu theta of x. So it produces this inhomogeneous term that exactly cancels the extra junk we get when the d mu acts on the theta term here. So that's sort of the miracle of the gauge symmetry. This extra photon field, this vector boson field, comes in to preserve this transformation that's different at different points in space and time. And this very, very non-trivial symmetry is actually the underlying principle behind the structure of this Lagrange density. Everything is cooked up to make this work. Okay, notice, for example, that the field strength tensors F mu nu, under this transformation, these terms here that you get, right, I will have a d mu acting on d nu of theta, but then I look over here, I will have a d nu acting on d mu of theta, but there's a relative minus sign between the two, and you'll see that F mu nu will not change under this gauge transformation, and so this term will also be invariant. So the whole thing will remain the same under this gauge symmetry, this U1 gauge symmetry. The reason I'm emphasizing this now is because it will be important when we talk about quantum chromodynamics in just a few minutes. Okay, now what do we do with this Lagrange density? Well, what we do is we apply the Euler-Lagrange equations. Okay, so the idea here is that we have this action, what's called the action. This is more of a classical way of just thinking of it, but the full quantum version of this is not that much different. So it's a good way of thinking about it. And what we want to do is we want to minimize the action or extremize the action. Okay, and so there is some configuration, some field A mu, where this action is stationary. In other words, we make a small change to A mu, and this action will not change at all. It's at a relative minimum. Okay, right? We have some minimum. When you're at the minimum, a linear change makes no change. The derivative is 0. So that's essentially what we want to do to solve for the equations of motion, to find the A mu that extremizes this action. If you do that, and you go through the Euler-Lagrange equation, you derive the Euler-Lagrange equations, and what you find is something like, for the case of the photon field, you get d nu, partial derivative of Lagrange density with respect to d nu A mu at the point x, like this, is equal to dl d A mu, like that. Right? And you can do the same kind of thing for the psi fields or the psi bar fields. Let's do it for the psi bar fields. We will have here, okay, d nu psi bar. Okay, so let's say some particular component of psi bar at the point x is equal to the derivative with respect to some particular component of psi bar at x. Okay, so these are the Euler-Lagrange equations. I can do the same thing for psi. All right, if I do that, and I look at this Lagrange density here, the first thing, let's do the psi bar first of all, because that's easier. You'll notice that there's no derivatives acting on psi bar anywhere, so this guy will actually be equal to 0. So the Euler-Lagrange equations for this will be that just the derivative, the partial derivative of L with respect to psi bar will be equal to 0. That's easy to do, though. I take the derivative with respect to psi bar, it's just this term without the psi bar. I take the derivative of this term, it's just this term without the psi bar. Okay? And that gives me exactly these equations of motion from that. All right? If I do the same thing for the photon field, then I take the derivative with respect to A mu. That gives me the term that looks like the current density. I get a psi e, I get an I gamma mu I e psi e. Okay? But then I also have to take the derivative with respect to partial derivative with respect to d nu A mu, and I get something that will be proportional to F mu nu. Okay, but then I have to take a derivative d nu acting on F mu nu, so I get something that looks like d nu F mu nu. I can do some simplifications though. If I fix a gauge, I'm not going to go through this, but you make a Lorentz gauge where you have that d mu A mu is equal to 0. That fixes that gauge. Okay, Lorentz gauge. It's a constraint. You make an additional constraint because the equations of motions are not solvable without making this additional constraint. Then what you find is you end up getting a very simple relation like this. This guy is this D'Alembert operator. D nu, or d mu, acting on A mu is equal to this current density. Okay. Let's go on. Now, so we talked about the current density, coupling to the photon field. So there's an interaction between the photon and these electrons, and so these give rise to this interaction. So remember, the psi e contains annihilation operators for the electrons, so you can imagine an electron coming in, and this guy will eat up the electron, okay? And this A mu has creation operators for the photon, so it can spit out a photon. But then it also has creation operators here for the electron from psi e, so that would maybe create an electron. Okay, so this is the vertex operator for quantum electrodynamics. And what I'm doing is I'm writing down the Feynman rules. Now there are also things like the photon propagator. That's just what a free photon does. It just propagates along. And then we also have the electron propagator. That's just for the free electron or the free positron. So then the simplest sort of diagram you can write down is something like this, where two electrons are interacting with each other. For example, there's some Coulomb repulsion between the two. That comes from the exchange of this photon. So you can then get this force law, that the Coulomb force law is 1 over 4 pi e squared over r squared, or alpha over r squared. However, there's a modification that comes about if you go to higher order in the Feynman rules, and you have, for example, a diagram like this where you can do something this is what's called vacuum polarization. You have this extra loop with the electrons going around in a circle with two vertices like this. And so you essentially have a virtual electron and positron pair being produced, and you can think of that as producing little dipoles from the vacuum. And this actually has the effect of a dipolar material, a dielectric material. At large distances, the effective strength of the charge is decreasing. It decreases. So even though we've measured the Coulomb interaction at long distances is alpha over r squared, at very short distances what you find is that the strength of the the Coulomb force gets stronger. So there's an effective strength to the coupling that gets stronger at shorter distances. So at large distances, the electric charge is screened, becoming weaker at larger distances. So therefore, at shorter distances, you see more of the sort of the bare charge, and it looks stronger. Now, one of the consequences of this is looking at something that's called the Casimir effect. So the Casimir effect is when you have two very straight metal plates or conducting plates that are parallel to each other with some small gap d between the two. And in between this gap, there's the effect of the vacuum having these virtual electron-positron pairs, and that gives you little dipoles, and these dipoles induce charges on the surfaces, the inner surfaces of these connecting plates, and as a result you get an attractive force between the plates. And this actually has been measured. It's what's called the Casimir force, and it's proportional to 1 over the distance to the 4th power. It's a very small coefficient though, so it's a small effect, but it's measurable. Another place this is seen is in what's called the lamp shift. The lamp shift describes the hydrogen atom. Okay, so we have, let's say, a hydrogen atom. We have a proton at the center, and we have an electron going around it. And so we know we have then the hydrogen atom, we have principal quantum number. N equals 1, we get the 1s state. N equals to 2, we get the 2s state, the 2p state. Now if you do a more sophisticated calculation, include the spin-orbit coupling, then we find that there will be some splitting. So we'll have then the 2s1 half, we'll have the 2p1 half, as well as the 2p3 half state. However, it turns out that still, even with that fine structure splitting, that these two guys will be exactly this, will have the same energies. Okay, so these have the same energies. However, it turns out that when you include the vacuum polarization diagram, there is a splitting between these, and that splitting can be measured, and that's really a beautiful application of quantum electrodynamics. And by measuring this lamp shift, you can make a prediction how strong this diagram is, and it works out beautifully with theoretical calculations. Now, let's turn our attention to quantum chromodynamics. So quantum chromodynamics has a structure that's rather similar to that of quantum electrodynamics, and so that's why we started with quantum electrodynamics. So you see here the similarities between what we had and what we have now with quantum chromodynamics. The difference is that in quantum chromodynamics, we have this extra index here, this J index. It's a color index. The Q stands for quark, but you can just ignore that because it's just to remind you that we're talking about quarks. So psi J, so J can be 3 possibilities: red, blue, or green. Okay, so I already told you that we have a column vector for all these Dirac components, but there's also going to be a column vector for the color components as well. So you can think of this as a tensor product of the Dirac components, 4 components for the Dirac field, as well as the 3 components for the colors. Now then, in this notation here, these T alphas are matrices. These are 3 by 3 matrices, and these are what are called the Gell-Mann matrices. Okay, these Gell-Mann 3 by 3 Gell-Mann matrices, and these are the generators of the SU3 group. Okay, so remember the terms here. U is for unitary, meaning that the matrix U, let's call it U dagger is equal to U inverse. The special, S is for special. That means that the determinant of U is equal to 1. And the 3 means it's a 3 by 3 matrix. So what's going on here is we have, in this case, an SU3 gauge symmetry. So in other words, we have some unitary matrix, some special unitary matrix, 3 by 3 matrix, with some components, I, J, that will depend on space, x, space-time, and that will act on our field psi J at point x, and we'll have a sum over the color indices J, and this will then be how my field will transform. So that will be my gauge transformation. So it was psi I, and it's going to then transform like this, where the transformation, this will be a 3 by 3, it will be a 3 by 3 special unitary matrix, or SU3 matrix. Okay, and in order to make this gauge symmetry work, this SU3 gauge symmetry, we need to have the coupling of these gluon fields. Okay, so I should mention more about these Gell-Mann matrices. They remember when we talked about the gauge, the Lie symmetry, the Lie groups, and we talk about the Lie algebra. So these T alphas obey these commutation relations: F alpha, beta, gamma, sum over gamma, T alpha. If I take the commutators of these 3 by 3 matrices, I get the structure to it, and these things are called the SU3 structure constants. Here, F alpha, beta, gamma. Okay, so I know this is getting a little complicated, but SU3, the group SU3 is a bit complicated. So what we have here is the coupling of the quark fields with, you can think of this as having the creation for the quarks, the annihilations for the quarks, as well as the creation for the antiquarks. And then you have the conjugate of that, which will give you the annihilation for the antiquarks, as well as the creation for the quarks. And then here are the gauge fields. So the mu is again a Lorentz index that can be 0, 1, 2, or 3, as before. But alpha is what's called the gluon index, so this can be 1, 2, 3. It goes up to 8. The reason it goes up to 8 is because there are 8 of these Gell-Mann matrices. There are 8 of these guys. Okay, so let's tell you the rest of the story here. Okay, so these guys are just derivatives. That's nothing special. This is the coupling. It looks the same as before. This looks very familiar. This is just the mass of the quark. These are the quark fields here. And then this is the gauge, the field strength tensor for the gluon fields. But because these guys are matrices rather than just simple numbers, it turns out that you end up getting commutators of these Gell-Mann matrices appearing in the field strength tensor. Okay, it's an added complication that will actually be essential in that the gluon fields by themselves, they involve terms that are not just simply quadratic in the gauge fields, but there will be terms that involve more powers of g mu. And we'll come back to that as being an essential difference between quantum chromodynamics and quantum electrodynamics. So everything else we've covered here. So we've talked about the color field strength tensors, the color potential, the vector potential for the gluon field, just the fields for the gluon fields. Sorry, just the gluon fields. Okay, and then the T alphas are the Gell-Mann matrices, and these F alpha beta gammas are the structure constants, and the psi I are the Dirac spinors for the quark fields, where I is the color component. And then we have the coupling. It works the same way. Alpha S is just g squared over 4 pi, and so g is the square root of 4 pi alpha S. Okay, now the crucial difference between quantum electrodynamics and quantum chromodynamics is actually the fact that we have this extra term here. Okay, so let me try to show you what that does to you. It changes the game completely. So we had terms like this, and we will again have terms like this. Just this time, this will be a gluon. So we'll have a coupling of our quark line with the gluon field. So we're doing now quantum chromodynamics. We're writing down the Feynman rules. Okay, and then we have the quark propagator, just like before, so everything's the same so far. And then we have the gluon fields. Now the big difference though is that when I take g mu nu and I write down another g mu nu alpha, like I have here, I'm going to get terms that will involve not just quadratic terms in g, I'll get cubic terms in g, as well as, just think of this squaring this term. I will get terms that will be not just quadratic in g, so that's what's expressed here, quadratic terms in g, 2 n's to the line if you want. But then I'll also have terms that will be cubic in g and quartic in g. So that will give these couplings as well. And this makes all the difference in the world. We have then the self-coupling of the gluons with themselves. So we have these extra things that were not there in the case of quantum electrodynamics. And next time, we will talk about the consequences of this. It will be a profound consequence. And I'll talk to you then on Friday about this.